Hello my precious friends and welcome to our today's class. It is our second lesson on the ninth topic of Form 3 work, which is called quantity of heat. As usual, let me commence by giving the quote of the day, which states that you can only gain something if you risk everything. We shall discuss that quote at the end of our class today. So today we are looking at determination of specific heat capacity of a solid. So two methods are involved. One, we have the method of mixtures. Two, we have the electrical method. But in our today's class, we are going to discuss the method of mixtures. So the setup below can be used to determine the specific heat capacity of a solid using the method of mixtures. The apparatus involved, one is that you need a thermometer for detecting the temperature change or for measuring the change in temperature. We also need a liquid. In this case, you are using water whose mass is known, that is MW, and whose specific heat capacity is known, that is CW. We also need a metal block or simply a mass whose mass is known. In this case, we are talking of MS, then whose specific heat capacity is the one that we want to determine. You also need some lagging material, some wooden box, and of course a calorimeter for maintaining or for preventing heat loss to the environment. So in this particular method of mixtures, a known mass of a solid, let's say MS, at room temperature is heated in hot water to a constant temperature, which we are calling the T final. Then the mass of the hot water in a lagged calorimeter is known. Therefore, since the specific heat capacity of water is also known, then the specific heat capacity of the solid can be determined by the law of conservation of energy. Remember, the law of conservation of energy requires that provided there is no heat which is being lost to the environment, then the heat which is lost must be equal to the heat gained. So to know the substance that is losing and gaining heat, you simply observe the temperature changes. You compare the initial temperature and the final temperature. So if a substance is in such a way that its initial temperature is larger than the final temperature, then it simply means that substance has lost heat. On the other hand, if the initial temperature is smaller than the final temperature, it means that that particular substance has gained heat. Because if a substance gains heat, we expect its temperature to rise. Conversely, if a substance loses heat, then we expect its temperature to reduce. So in this particular case, because we are simply taking a metal block which is initially at room temperature, it simply means then we are taking the metal block we are putting it into hot water. It simply means that in this case, the hot water will actually lose the heat. Therefore, the heat being lost by the hot water must be equal to the heat which is being gained by the solid. Remember, the solid was dropped in the hot water at room temperature. So the water will lose some heat, then the heat that is lost will be gained by our metal block or the solid. So from the law of conservation of energy, all the heat which was lost by water must be equal to all the heat which is being gained by the solid. That is, provided that no heat is being lost to the environment. Then of course, the heat which is lost by water will simply take the mass of water multiplied by the specific heat capacity of water times the change in temperature for water. So MC theta, water, that represents the heat which is being lost by water, so must be equal to the heat which is gained by the solid will be equivalent to the mass of the solid multiplied by the specific heat capacity of the solid multiplied by the change in temperature for the solid. Therefore, if we want to find the specific heat capacity of the solid, we'll simply divide both sides by mass of the solid and the change in temperature for the solid. Therefore, the specific heat capacity of the solid will simply be equal to mass of water multiplied by specific heat capacity of the water multiplied by the change in temperature for the water divided by the mass of the solid multiplied by the change in temperature for the solid. Then, when performing experiments which are involving determination of specific heat capacity using the method of mixtures, the following precautions need to be taken into consideration in order to minimize heat losses to the surrounding. So the first precaution that you should take in order to prevent heat loss to the environment is that you use a lid of a poor conduction. In this case, you are using the cover, that is the cardboard cover. So you can see we have our cardboard cover on the top end here. So remember, a cardboard is simply an insulator or a poor conductor of heat. Therefore, this prevents loss of heat through the method of conduction. It prevents heat loss through conduction. The other precaution is that you are supposed to use a highly polished calorimeter. So the calorimeter needs to be highly polished. Remember, polished material are usually shiny materials. So the purpose of polishing or using a highly polished calorimeter is simply to prevent heat loss through radiation. Because we did say that under heat transfer or also thermal conduction, we did say that shiny materials emit heat away from it. So when the calorimeter is highly polished, it simply means that all the heat that is within that particular calorimeter will be reflected back. Therefore, it won't be lost to the environment. So the purpose of using a highly polished calorimeter is to prevent heat loss through radiation. Then heavy lagging of the calorimeter. So to lag simply means that you add some materials which are poor conductors of heat. So you can see these are our lagging material which are placed in between the calorimeter and of course the content within that particular calorimeter. So the lagging material simply prevents heat loss to the environment. The lagging material are usually poor conductors of heat. Then of course we have said the purpose of the thermometer is simply to detect any temperature change. Next, we look at our first example. So the first thing, we simply highlight the key information that we have been provided by the question. So we are told that a lagged copper calorimeter of mass 0.75 kg. So the mass of the copper calorimeter we are given as 0.75 kg. So I simply represent it by mass of the copper calorimeter, contains 0.9 kg of water. So we are also given the mass of water, which is equals to 0.9 kg of water at 20 degrees Celsius. So that is the initial temperature for the water. So, but because the water is in the copper calorimeter, it simply means that the initial temperature for the copper calorimeter will be equal to the initial temperature for the water because they are in the same container. So to understand this better, for example, consider tea, which is being placed in a metallic cup. So you realize that if the temperature of the tea is 20 degrees Celsius, the temperature of the cup will also be 20 degrees Celsius. That is, the material which is keeping our hot water will assume the temperature of that particular water. Therefore, the initial temperature for water is equal to the initial temperature for the copper calorimeter, which is simply equal to 20 degrees Celsius, which is equal to the 20 degrees Celsius. Then we are also told that a bolt of mass 0.8 kg, so mass of the bolt is 0.8 kg, is transferred from an oven at 400 degrees Celsius. So that is the initial temperature for the bolt, 400 degrees Celsius to the calorimeter, and a steady temperature of 50 degrees Celsius is reached by the water after stirring. So this simply means that the 50 degrees Celsius is the temperature of the mixture. That is the final temperature of the mixture after stirring. So the final temperature of the mixture is simply 50 degrees Celsius. Then we are required to calculate the specific heat capacity of the material of the bolt. Then we are given that the specific heat capacity of the copper is 400 joules per kilogram per Kelvin, and that of water is simply 4,200 joules per kilogram per Kelvin. So to tackle this question, we'll simply use the law of conservation of energy, which requires that the total heat which is lost must be equal to the total heat which is being gained. That is, provided that no heat is being lost to the environment. Then from there, you identify the substance that is gaining heat and the substance that is losing heat. What helps you to differentiate that, you simply look at the initial and the final temperature. For example, our final temperature in this case is the 50 degrees Celsius. So any substance that has an initial temperature which is less than 50 degrees Celsius, then that substance must be gaining heat. Because when a substance gains heat, that is when its temperature rises. Then any substance that has an initial temperature which is greater than 50 degrees Celsius, it simply means that substance is actually losing heat. Because when a substance loses heat, its temperature reduces with time. So in this case, the bolt is actually losing heat. So it is losing heat because its initial temperature is 400 degrees Celsius, but the final temperature after stirring is 50 degrees Celsius. So this simply shows us that the bolt actually loses heat from 400 degrees Celsius up to 50 degrees Celsius. Therefore, the heat that was lost by the bolt must be equal to the heat that was gained by both the calorimeter and also the water. So remember, the calorimeter and the water, they are gaining heat because the initial temperature was 20 degrees Celsius. Then if you look at the final temperature, it is actually 50 degrees Celsius. That is the final temperature of the mixture. So that shows you that the water and the calorimeter, they gained heat from 20 degrees Celsius up to 50 degrees Celsius. So we are saying that the copper calorimeter and the water gained heat because their initial temperature is smaller than the final temperature. Conversely, we are saying that the bolt lost heat because its initial temperature is larger than the final temperature of the mixture, which is the 50 degrees Celsius. Therefore, the heat lost by the bolt is equal to the heat gained by the copper calorimeter plus the heat gained by the water. So, of course, heat lost by the bolt is simply given by mass of the bolt multiplied by the specific heat capacity of the bolt multiplied by the change in temperature for the bolt, which must be equal to the heat which is gained by the calorimeter is given by mass of the calorimeter multiplied by specific capacity of the calorimeter multiplied by the change in temperature for the copper calorimeter. Then plus heat gained by water is given by mass of the water multiplied by the specific heat capacity of water multiplied by the change in temperature for the water. So the mass of the bolt we were given as 0.8 kilograms. So 0.8 multiplied by specific heat capacity for the bolt, which is what we want to find. So we simply represent it by specific heat capacity for the bolt multiplied by the change in temperature for the bolt. So the change in temperature, you simply take the larger temperature minus the smaller temperature. So for the bolt, the initial temperature was 400, then the final temperature of the mixture is 50. So the change in temperature for the bolt would simply be 400 degrees Celsius minus 50 degrees Celsius. So 400 minus 50, which will simply give us 0.8 times specific heat capacity for the bolt multiplied by 400 minus 50. You'll simply obtain 350 Kelvin or 350 degrees Celsius. Remember from our previous class, we did prove that the change in temperature, whether it is in degrees Celsius or in Kelvin, actually the value will be the same. Then the heat gained by the calorimeter, we simply take the mass of the copper calorimeter, which we were given as 0.75 kg, multiplied by the specific heat capacity for the copper calorimeter, we were given as 400 joules per kilogram per Kelvin. Remember, specific capacity of the copper is simply represents the specific heat capacity of the calorimeter because we are talking of a copper calorimeter. Therefore, the specific capacity of the copper calorimeter we are given as 400 joules per kilogram per Kelvin multiplied by the change in temperature for the copper calorimeter. We'll simply take the final temperature minus the initial temperature. So T final for the mixture was 50. Initial temperature for the copper calorimeter was 20 degrees Celsius. Therefore, 50 minus 20, you will simply obtain a temperature change of 30 degrees Celsius or 30 Kelvin. Remember, when we are talking of a change in temperature, we are not interested with the sign, whether it is positive or negative. You simply take the larger value minus the smaller value. So this will give us then the heat gained by the water. We simply take the mass of the water, which we were given as 0.9 kg, multiplied by specific heat capacity for the water is always 4,200 joules per kilogram per Kelvin, multiplied by the change in temperature for the water. Remember, the change in temperature for the water is the same as that of the copper calorimeter because actually they were at the same initial temperature, and of course the final temperature is for the whole mixture. So the mixture involves the copper calorimeter, our bolt, that is the solid, and of course also the water. Therefore, the change in temperature for the water will simply take the final temperature 50 minus initial temperature, which is 20. So 50 minus 20, you will get 30. So 0.9 times 4,200 times 30. So at this particular stage, if you take 0.8 multiplied by 350, you will simply obtain 280. Then of course times specific capacity for the bolt, which is equals to 0.75 times 400 times 30, you'll obtain 9,000. Then plus 0.9 times 4,200 times 30, you'll obtain 113,400. Then of course 900, that is 9,000 plus 113,400, you'll obtain 122,400, which is equals to 280 multiplied by specific capacity for the bolt. So to find specific capacity for the bolt, we'd simply divide both sides by 280. So specific capacity for the bolt is equals to 1200 and that is 122,400 divided by 280, which gives us 437.1 joules per kilogram per Kelvin. So notice that this one is correct to 4 significant figures. Next, let's look at our second example, which reads that 700 gram of a solid. So this is the mass of the solid. So M solid is simply equal to 700 grams. We convert each quantity into its respective SI unit. We know that the SI unit for mass is the kilogram. So to convert 700 gram into kilogram, we simply divide it by 1000. So mass of the solid is 0.7 kilogram. Then at 20 degrees Celsius, so this is the initial temperature for the solid. So T initial for the solid is equals to 20 degrees Celsius, was slowly dropped into water at 60 degrees Celsius. So that is T initial for the water was actually 60 degrees Celsius, and stirred carefully until a constant temperature of 52 degrees Celsius was actually attained. So 52 degrees Celsius represents our final temperature of the mixture because it is obtained after stirring. So stirring simply means helps those substances to mix, therefore having a common final temperature. So if the mass of the water was 600 gram, so M water is 600 gram. Of course, to convert 600 gram into kilogram, we simply divide it by 1000. So 600 divided by 1000 times 1 kg, you'll obtain a mass of 0.6 kg. Then determine the specific capacity of the solid. So we need to find specific capacity of the solid, that is C solid. Then we are told to ignore the heat which is absorbed by the copper, that is by the calorimeter. Remember, in our first example, we were given the values which were having the copper calorimeter. So if you are given the values involving the calorimeter, you simply include the calorimeter in your calculation. But if you are not provided with the values of the copper calorimeter, you simply ignore it. It simply means that the heat that was absorbed by the copper calorimeter is ignored in that particular case. So from the law of conservation of energy, heat loss must be equal to the heat gain, provided that no heat is being allowed to go to the environment. Therefore, the substance losing and gaining heat, we simply observe the initial and the final temperatures. So the T final is 52 degrees Celsius. So that means any substance that has an initial temperature which is less than 52 degrees Celsius, then that substance must be gaining heat. So in this case, the solid is gaining heat. Then any substance that has an initial temperature which is greater than 52 degrees Celsius, then that substance is losing heat. So because water has an initial temperature of 60 degrees Celsius, which is greater than the final temperature of 52 degrees Celsius, it simply means that the water in this case is actually losing heat. Therefore, the heat that is lost by water must be equal to the heat that is gained by the solid. Remember, we are not adding the heat that is either gained or lost by the calorimeter because we are told to ignore the heat that is absorbed by the calorimeter. Therefore, the only substance gaining heat in this case is actually our solid. So heat gained by lost by water is given by mass of water multiplied by specific capacity of water times the change in temperature for the water. Then the heat which is gained by the solid is given by mass of the solid multiplied by specific capacity of the solid multiplied by the change in temperature for the solid. So the mass of the water we are given as 0.6 kg. So 0.6 multiplied by specific capacity of water we are given as simply 4200 joules per kilogram per Kelvin multiplied by the change in temperature for water. We'll simply subtract the initial temperature for the water, which was 60 degrees Celsius, from 52 degrees Celsius. So the change in temperature, we are not concerned with the negative sign. So we simply take 60 minus 52 such that we get a positive value. So the initial temperature for water was 60. The final temperature is 52. So 60 minus 52, that will give us a temperature of 8 Kelvin or 8 degrees Celsius. So 0.6 times 4,200 multiplied by 8 Kelvin, you will simply obtain 20,160. Therefore, at this stage, let's look at the values involving the our solid. So mass of the solid is 0.7 kg from here, multiplied by specific capacity for the solid, which is C solid, multiplied by the change in temperature for the solid. We simply take the initial temperature for the solid, we subtract it from the common final temperature of the mixture. So 52 minus 20, you will simply obtain a temperature change of 32. So 52 minus 20, that will give us 32. So 0.7 multiplied by 32 will simply obtain 22.4, then multiplied by specific heat capacity for the solid. So if 20,160 is equals to 22.4 multiplied by specific capacity for the solid, if I want to make specific heat capacity for the solid subject of the formula, I'll simply divide both sides by 22.4. So specific capacity for the solid is equals to 20,160 divided by 22.4, which will simply give us 900 joules per kilogram per Kelvin. Therefore, the specific heat capacity of the solid was 900 joules per kilogram per Kelvin. Lastly, I have an exercise which I recommend you should try to your own free time to gauge whether you have understood the questions that you have just dealt with. Of course, if you have any challenges in handling any of the question, feel free to drop a comment specifying the question that you need help in. And of course, as usual, I'm always here to try and help where possible. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that you can only gain something if you risk everything. So the quote is encouraging us to be risk takers in life. Most of us miss opportunities in life just because we are afraid of taking action. Remember that unless you try and fail, you will never know how great you will have become. Therefore, embrace failure because it's the only way we can learn to overcome the challenges of life. And lastly, recall that risk-taking, failure, and self-awareness are essential components of true success. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you'll get notified. Thank you. Until next time, this is Kind Tuition Academy.